Why are multiplication patterns found in Pascal's triangle? Imagine a triangle made of numbers that keeps revealing surprising connections to multiplication. It might look simple at first, but it hides many patterns linked to how numbers grow and combine. Pascal's triangle is built by starting with a 1 at the top, then adding numbers diagonally to fill the next row. Each new number is the sum of the two numbers directly above it. Even though it's made by adding, it's full of multiplication secrets waiting to be uncovered. Every number in the triangle is called a binomial coefficient. These coefficients tell us how many ways we can choose a certain number of items from a larger group. To find these coefficients, mathematicians use factorials, which are just the multiplication of all numbers from 1 up to a certain point. For example, to find the number of ways to pick 3 items from 5, you multiply 5 times 4 times 3, then divide by the factorial of 3. So, even though the triangle is built with addition, the numbers themselves are deeply connected to multiplication through these factorial formulas. One of the clearest multiplication patterns appears in binomial expansion. When you expand a binomial expression like a plus b raised to the power of n, the coefficients of each term match the numbers in Pascal's triangle. This means that multiplying out these expressions involves multiplying the coefficients, which are the triangle's entries. It's like the triangle is a shortcut to understanding how multiplication works in polynomial expressions. Another pattern shows up when you multiply all the numbers in a row. The product of the numbers in a row relates to factorials, which are all about multiplying sequences of numbers. These products can help approximate constants like the number e, which is fundamental in growth and decay processes. So, multiplying the row entries connects the triangle to some of the most important ideas in mathematics. The sum of all the numbers in the nth row equals to raised to the power of n. This pattern demonstrates exponential growth, which involves repeated multiplication. Early rows also reveal powers of 11 when you read the numbers as digits, showing how the triangle encodes multiplication relationships in a hidden way. Finally, binomial coefficients are used to calculate combinations, which are ways to count how many different groups you can form from a larger set. These calculations involve multiplying and dividing factorials, again linking back to multiplication. The triangle helps us visualize these processes easily, making complex counting problems simpler. In all these ways, Pascal's triangle shows us how multiplication is woven into the fabric of number patterns. The triangle's simple addition rule hides a world of multiplication relationships, revealing how these core operations work together to create the beautiful structure we see. It's a perfect example of how basic mathematical ideas can combine to produce intricate and meaningful patterns.